going to start our study of physics the way I learned it in high school back in the dark ages. My physics teacher started out with this question: what is 2 plus 2? And we all said 4. And then he said, is it always? And here we have two examples. In the first example, a student walks 2 miles north, then walks 2 miles east. I just want to know the distance he has walked. Okay. Well, he went 2 miles north, and then he went 2 miles east, and that's going to give me a total distance of 4 miles. So in that case, 2 plus 2 did equal 4. But if I ask the question slightly different, what is not the distance he walked, but the displacement? Displacement is defined as the position relative to his starting point. So for that, it's a little more tricky. We can draw his starting point, and then we're going to draw that he went 2 miles north, and then he turned and he went 2 miles east. Now he's obviously not 2 miles away from his starting point. So we could draw that in here. So this is where he is relative to his starting point. Okay, we're going to call this d for displacement in this case. Okay, and how would we find the length of that? Well, we could use Pythagorean theorem. So d squared is equal to 2 squared plus 2 squared. So 2 squared is 4, 4 plus 4 is 8, so d squared equals 8. And then take the square root, and we get d is 2.83 miles. And if I want to know his position relative to his starting point, I also have to say what direction he is relative to his starting point. Now this one's pretty easy. Since these two sides are the same length, I know that this is a 45-degree angle here. Okay? So I could say that he is at 45 degrees north of east. My reference for that then is this dotted line going east, and he's 45 degrees north of that. So this is his displacement. Now, the reason that was different, okay, is sometimes directions are important, sometimes they're not. If I want distance, direction's not important. I just need to know that he went 2 miles, then 2 miles. But if I want displacement, direction is important. Okay? And the difference types of numbers. There is a scalar, and scalars have only magnitude. They don't have direction, they only have magnitude or size. So the magnitude of the distance he walked was 2 miles and 2 miles for a total of 4 miles. And scalars I can just add like that. They're normal numbers. But vectors are quantities that have both magnitude, so they have a size as well, and they have a direction. So displacement, this one here where we had to worry about direction, is a vector, whereas distance is a scalar. I don't have to worry about directions. Now when I represent vectors, I represent them as arrows, just like we did above. And the length of the vector is represented, represents its magnitude. And the direction is obviously represented by which way the arrow is pointing. So first we're just going to practice representing some vectors. Okay. So in the space below, from a common origin, draw the following vectors. And we have 1 meter using a scale of 1 meter. 5 meters is 1 centimeter. So the first one's 20 meters west. If it's a scale of 5 meters per centimeter, then this is going to be 4 centimeters long. Okay. Now it says go from a common origin, so I'm going to put a point someplace down here. And the first one is west, and I had to draw it 4 centimeters long. So I'm going to take my ruler, and you may want to take some time to grab yourself a ruler. And I'm going to drag my ruler down here, slide it over. I'm going to make it 4 centimeters long, pointing to the west, so going this way. Okay, so that's the first vector, and I want to label. Okay, that the length of that is 20 meters. Now the second one is 40 meters north. So 40 meters, using my scale, it's 5 to 1. So 40 meters, 40 divided by 5 is going to be 8. So I need to make that 8 centimeters long. Okay, so now I'll take this and spin it. bring it over here and make my vector 8 centimeters long. So I'm going from 8 to 16. So from here, I would go up to 16 like so. Okay, and I would say that that one is equal to 40 meters. Now, the last one I have to represent is 25 meters, 40 degrees north of west. So what does that mean? Okay, north of west, that means west is my reference. The second number, north of west, the second word is west, that's my reference. And then I'm going to go north of that. So I need to take my protractor, I'm going to drag that over here, okay, so that the origin of the protractor is at the origin. Now my reference was west, so my reference is along this line here, and then I have to go 40 degrees north of that. So I'm going to take and I'm going to mark 40 degrees north of that right here. I'm going to move my protractor back out of the way. Okay. Now it's 25 meters. Again, our scale is 5 to 1, so I'm going to have to make this equal to 5 centimeters. So I will take my ruler again. Okay. And then I have to put it at the origin. I'm going to have to rotate it. So that it is going through that point. Take a little more. Okay, so now it has to be 5 long, so if I'm starting at 6, I have to go to 11, and I would go right along here. And I would label that one is 25 meters. Okay, now we're going to learn how to add vectors. This comes into play when you're doing something like this. Okay, now one type of vector is a force, which is a push or a pull. And the units for force are newtons. So let's say I have something pulling me this way with a force of 20 newtons. And something else pulling me this way with a force of 40 newtons. Okay. Now which way am I going to go? Well, I'm going to end up going someplace in between there, all right? And I have to figure out where that's going to be. And there's a couple ways to do it. The first way we're going to talk about is using a scale model, okay? And you have to move the vectors so they are tip to tail. Okay, if I look at a vector, this is the tip, this is the tail. Now when I look at the object and the vectors pulling on it, the two tails are touching each other. And I have to move them so that they are tip to tail. So I have to move one of the two vectors. I could pick either one. I'm going to pick the 20. I'm going to move the 20 so that its tail is at the tip of the 40. So it would look something like this. I have the 40 going this way. And I take that 20 and I'm going to slide it over here. Okay? And it's going to end up pointing back this way. Okay? And there's my 20 right there. Right? Then, the last thing is you draw in the resultant from the origin to the tip of the last vector. So my resultant is going to be from the origin where I started to the tip of the last vector I drew. And that we're going to label R for the resultant. And back here we said, well, we think it's going to go up this way someplace. If I do it out, sure enough, it is going up and right, just like I said it should back here. Now, in order to do it correctly and get a good value, we have to use a scale model, is one way. We're going to learn how to do it using components in a little while. And then in pre-calc, you might use the law of cosines to do it, but we're not going to do that in here. Top of the next page is some examples. All right. So we have two forces. Okay. One is 20 and one is 30, and they're acting on an object, and I'm trying to find the resultants. Well, the first thing is if they're both pointing east. So here's my object, and I have a 20 pulling on it, somebody pulling on it with a force of 20 newtons, and another one pulling with a force of 30 newtons. In this case, I don't really have to draw a scale model because it's going to be pretty obvious. They're working together, they're helping each other out. So the resultant, I can just add them. It's going to be 20 plus 30 is 50 newtons to the east. So if they're in the same direction, you're just going to add. Now, the next one, I could say I have 20 newtons east and 30 newtons west. Well, that's not going to be as effective. They're working against each other. And which one's going to win? Well, the 30 is going to win because it's bigger, and that's going to give me a resultant of 10 newtons west. So if they're in opposite directions like that, I just subtract. The third one's also pretty easy. I have 20 newtons east, and then I have 30 newtons north. Okay. Now remember, I know it's going to go someplace in between these two. You don't have to draw this line, but I know it's going to go up here someplace, right? And I have to figure out what it's going to be. So I have to draw them so they're tip to tail. Right now, the two tails are touching each other. So I have to move one or the other. I'm going to move the 30. I'm going to slide the 30 over, and now the 20 is going to be down here, and the 30 is going to be over here. Then if I'm trying to find my resultant, I draw it from the origin to the tip of the last vector I drew. So there is my resultant. I'll label that R for resultant. And how are we going to find the size of that thing? Well, since these are at right angles, east and north are at right angles to each other, I can just do Pythagorean theorem. So R squared equals 30 squared plus 20 squared. Okay, and that's going to give, after I do my math, of a resultant of 36.1 newtons. Now, I also have to tell the direction. Up here, it was pretty obvious for the first one, okay, that if these are both pulling east, it's going to end up being east. The second one, the west one, so it's west. This is a little bit harder. What I'm going to have to do is find this angle right here. So we'll label that angle theta. All right, and I can use tangent because I have the opposite and the adjacent side. Here's my opposite side. Here's my adjacent side for that angle. So I would do tan theta is equal to the opposite over the adjacent. So tan theta equals, the opposite is 30 divided by 20. So then theta would be the inverse tan of 30 over 20. When I do that, I get a value for the angle of 56.3 degrees. And it is north of east because my reference line here, my 20 is going straight east, and I swing north of that to find R. So we'll say north of east. Now I'm going to hold off for this bottom one until the next video.